Good morning, everyone. Today, we will be studying Chapter 4, Consensus Algorithms. This chapter is primarily composed of 5 sections. First, let's introduce Section 1, the background of distributed consensus algorithms. The core of blockchain is how to achieve distributed consensus and maintain a consistent ledger. Distributed refers to a system where the operation is carried out by all the nodes within the system, working together to perform the system's functions, and it is implemented across the various nodes. Consensus means that all participants reach a unified decision. This section will explain the background of distributed consensus algorithms by discussing the Byzantine generals' problem regarding consistency in distributed systems, the basic definition of consensus systems, and the FLP theorem. In the ancient Byzantine Empire, the generals of the army had to unanimously decide whether to attack a certain enemy army because only through unified action could they achieve victory. If there were traitors among the generals, the traitors could take actions to deceive some of the generals into attacking or prevent them from making a decision. The lack of unified action would inevitably result in the defeat of the army. So what is Byzantine fault tolerance, BFT? Byzantine fault tolerance, BFT, is a fault tolerance technology in the field of distributed computing designed to better perform proof of work and validation algorithms. The Byzantine assumption models the real world, where computers and networks may behave unpredictably due to hardware failures, network congestion or interruptions, and malicious attacks. Byzantine fault tolerance technology is specifically designed to handle these abnormal behaviors. Practical Byzantine fault tolerance, PBFT, algorithms are developed for distributed systems primarily based on state machine replication, aiming to allow the majority of honest nodes in the system to override the behaviors of malicious or faulty nodes. In PBFT, the number of nodes is fixed, and each node represents one vote. Through a majority rule, the algorithm achieves Byzantine fault tolerance. The maximum fault tolerance is limited to no more than 1/3 of all nodes. That is, if more than 2/3 of the nodes are normal, the entire system can still function properly. Now, what about the Byzantine generals' problem? It is a well-known consensus problem that describes the issue of consistency in distributed systems. It was first proposed by Lili Limpo and others in 1982, and it is referred to as the Byzantine generals' problem or Byzantine fail. In the context of the Byzantine problem, if there are n nodes in total and f traitor generals, the problem can only be solved when f is greater than or equal to 3f plus 1. Considering the more consistent scenario, when the proposer is not a traitor, they send a proposal with the value of 1 to other nodes in the system. At this point, there will be n-f verified proposals in the system. Since the traitors will try to interfere with the system, there will be f uncertain proposals. Only when n-f is greater than f, or when n is greater than 2f, can the system reach a final consensus. When the proposer is a traitor, they will attempt to send the opposite proposal to the n-f normal nodes, i.e., they will send n-f divided by 2 proposals with value 1, and n-f divided by 2 proposals with value 0. The normal nodes in the system will receive n-f divided by 2 proposals with value 1 and n-f divided by 2 proposals with value 0. So, we say that the PBFT algorithm's operational steps can be divided into 1. Select one replica as the primary node, with the other replicas serving as backups. 2. The client sends a service operation request to the primary node. 3. The primary node broadcasts the request to the other replicas. 4. All replicas execute the request and send the results back to the client. 5. The client waits for F+1 different replica nodes to return the same result, which becomes the final result of the operation. Next, let's analyze some of the issues with the PBFD algorithm. Its main problems are related to computational efficiency, as it depends on the number of nodes participating in the protocol. It is not suitable for blockchain systems with a large number of nodes. The issues are primarily reflected in 1. Poor scalability of the system. 2. Fixed number of nodes, making it unsuitable for the open environment of a public chain. It is only applicable to consortium or private chains. 3. The PBFD algorithm requires the total number of nodes, n, to be greater than or equal to 3f+1. The number of failed nodes cannot exceed 1/3 of the total network nodes, which results in a relatively low fault tolerance. In distributed systems, the following characteristics are present. Processes have concurrency. There is no global clock, components can fail, and messages can be delivered at any time. Thus, nodes in a distributed system cannot guarantee fault-free operation with ideal performance. Node communication may fail to arrive on time, and response speed and throughput will be limited. There may even be malicious nodes that intentionally forge messages and disrupt the normal operation of the system. Here, we introduce the famous CAP theorem. The CAP theorem states that a distributed system cannot simultaneously satisfy the following three conditions: consistency, availability, and partition tolerance. In theoretical computer science, the CAP theorem is also known as Brewer's theorem. It states that for a distributed computing system, it is impossible to satisfy all three of the following simultaneously. Consistency, meaning all nodes access the same up-to-date copy of data. Availability, providing high availability for data updates. And network partition tolerance. In practical terms, partitioning refers to communication implementation. If the system cannot achieve data consistency within a time limit, it means a partition has occurred. In such a case, a choice must be made between consistency and availability for the current operation. According to the theorem, a distributed system can only satisfy 2 out of the 3 conditions, but not all 3. The basic definition of a consensus system also includes the following properties. Correctness. The value that honest nodes eventually reach consensus on must be one proposed by honest nodes. Consistency. All honest nodes must reach consensus on the same value. Termination. Honest nodes must eventually reach consensus on some value. From another perspective, we can also describe it using safety and liveness, where correctness and consistency determine the safety of the consensus, while termination represents liveness. The proper functioning of a consensus mechanism also requires the establishment of several basic models: network models, corruption models, and adversary models. All right, everyone, that concludes the content for today, which was section 1 of chapter 4.